wasn't gonna, you know.
All right, so let's see. Last time we talked about, what did we talk about? We talked about some capacitors and debalancing again, as I recall. We talked a little bit about transformers again, some diodes with the diode steering to make a full wave rectifier. And then we talked a little bit about the guts of the computing machinery, how it all works. And then we talked a teeny bit about an I/O cell. So it's an input-output cell or an I/O port that we would use to write a bit out to a wire. And I'm going to introduce you to a lot of concepts today, because depending on, so now we're into a point where we're doing things that you want to do with these things, right? And light lights and do stuff. And I'll tell you now that if you want to write good code that does things, you need to get intimate with the processor. So on a Arduino Uno, it's an Atmel, now Microchip bought Atmel about a year, 2 years ago. But it's an Atmel AT Mega 328 is the chip. You've got a do there, I think, or a...
Mine's an
it's a
Atmel
Mega-
2560.
Yes, 2560.
So it's an AT Mega 2560.
Right.
I don't know nothing about that chip, but it's going to be real similar to this, because when Microchip is famous for their PIC family, their PICs, at least in a class, run the same. They do things the same way. The same engineers built this chip, built this family of chips, built that family of chips. So they're very, once you learn one of them, there's other, there's little differences, but a lot of it's the same.
Well, I like that they tended to have their stuff standardized too. Like if it was pin 13 was the same across all the boards from what I was reading.
Oh, you mean across the
Yeah,
With
the
Arduinos.
little pins.
across the Arduinos?
Yeah.
Yes. At the microcontroller level, which is that little chip right there on this one, not so much. But the way they do the internal architectures is very similar. Microchip bought Atmel, but the Atmel line is going to stay the Atmel line, and the PIC line is going to stay the PIC line. And what you find is, I would say that personally, my experience is that the PICs are much more robust. As far as once you get them working, they're not going to break. They are signal strong. They run a little slower. The AT series, the Atmels, they run faster. They're a little easier to set up, but they're not as robust. I find that the way, when you're down at the bit level, working with individual bits and registers, I like the way the PICs work a little better. That's just my preference. What you're doing, the chip, if you ever go away from the Uno or whatever, and this little board, and you want to get down to rolling your own, then you choose a chip based on what you need. The ATs, they have their AT Tinies, and they have basically the same core, but there might only be 8 pins. So
Right.
you can do a lot with 8 pins, especially if you're using SSI and things like that. So we'll get to. So last time we talked about, and I did look this up. This is a Harvard. No, this is not the Harvard architecture. The Harvard architecture does split the program memory and the data memory. These guys, they roll the program and the data into the same in the flash, but then when you use it, it's only program memory. So there's some various. Anyway, we talked about there's a core, and there's some memory here. So this is flash. and this is your instructions. This is what you program it to do. And then we'll have port A, and then there's port B, and so on. These are generally 8-bit ports. What you'll notice using the Arduino IDE, there's no direct write to a port. You can write to a bit, right? There's a digital write, a pin number, and whatever. So one of the things I will show you today is how to write a whole port all at once. There is, and we talked about these yesterday, that if you take, or last time, so there's one, if I do this in slices, that's a half, that's a half. So I've got 8 bits. If I take one of these bits, there is a input buffer and an output buffer, and there's a register here. Something like that. And then there's a switch here that's controlled by another bit off here, so another register. And then there's another switch here. Controlled by yet another register. So what is this? This is 100K ohms, if I remember right. This is your data, so this is a read-write. So when I want to, so the first thing you had to do in your code was you had to tell it whether it was an input or an output. So in Arduino, in the Arduino IDE, that's pin mode, if I remember right. And then you would choose, let's say this is pin 13, just, I don't know if it is or not. So you'd say pin 13, and you'd say output. Now, we'll talk about what this is. This is something that is defined somewhere else. We're using the C language, or actually C++, which is an extension of C. I highly encourage you to do this. When you have, I'm going to use pin 13 in 6 different places in my code. Up here at the very top, pound, define. And you can say out pin, you can name it out pin or something like that. And now everywhere in your code where you would do this, you can say out pin.
It looks like more than 2 people are trying to figure out electrical circuits. They got all sorts of gadgets around. Is that all we got to show up?
Are you here for the class?
Not really, just to see what's going on.
No, I'm teaching the class.
Oh, you're the wizard electrical
I
engineer.
am no wizard.
Well, I've been doing this for over 30 years. If I haven't figured out how to move electrons through a wire by now, I better give it up.
Me too. So what this lets you do is, now instead of having to travel through all your code and find pin 13, pin 13, pin 13, and change it to pin 2, now you can do it in one spot. So I highly encourage you to use pound defines at the first thing in your, well, the very second thing in your code, but for right now it's probably the first thing, so that you get into this mode of giving things readable labels everywhere. And that way it will save you so much pain later.
So is that like a variable you're defining basically?
This is
Or constant?
it's not even that.
Yeah.
This pound define this pound in front of it is a preprocessor directive. So what happens in the C code, the compiler does a pass through and it says, oh, anywhere I see out pin, I put the number 2. And the very first pass it does is it goes through everything and it replaces out pin with the number 2. So that's not even really code per se,
Yeah.
it's a directive.
Right.
So would you put that before your void setup or inside of your void
I
setup?
would put it all the way at the very stinking top.
Yeah, it's outside of all the voids.
So the next thing, and this is if I'm doing raw C code, I have a void main. And so let's understand what some of these things are that we're messing with, right? My intent isn't to teach you C, but to give you just enough of a oomph to let you understand, and you can come ask me questions later or something like that. So a function is a collection of code that can stand alone by itself and can be called to do something. In C, the main program is called main. Every function has the ability to return a value. So when you see void main, the first thing this tells you is the main function does not return a value. That's what void means. It does not return a value. In fact, if there's nothing in here, that's actually a void. It's an understood. You don't actually write it usually, but it's an understood. Then when you see the open curly brace and then a close curly brace, whatever this function is, these lines of code are grouped together under void main. So what you see in the Arduino IDE is you see two functions. You see setup, right? And you see loop, I think it's called, right? And so there's a loop. My curly braces are broken. So what this really is, you've just written two functions. Off here on the side, somewhere where you can't see it, there's void main curly bracket, and it calls setup, and then it calls loop. End of
That's a
program.
good thing you're doing because Arduino masks all this and people don't know what's going on under the hood.
Well, likely is it calling loop in a like while true type
Yeah.
deal, like
Yeah.
literally looping.
Yeah, so yeah, you're right. It probably says while one
Yeah.
Loop. And then close brackets. So the next thing we'll talk about is in C, the end of line character that says the end of instructions is a semicolon. So if you see one of those, that means it's the end of a line. I can go loop, and sometimes your compiler will choke on it, but all that really means is end of statement, end of statement, end of statement, end of statement. That will compile just fine and do nothing. More than that, usually, not all compilers. And remember, things go in the order you tell them to go. It's going to do exactly what you tell it, exactly the way you told it, even if that's not what you meant to tell it, right? Okay. So, when you're writing these functions, so setup, in your setup function, you could have big chunks of stuff. A real good rule of thumb is if you ever see yourself doing something more than once, turn it into a function. So I won't use, or to compactify things to make it smaller. Because you can have setups that are this long, and well, maybe it makes sense, you know, this piece of that setup does one thing, so maybe you just pull that all together and call it a function. So generally speaking, you can have the basic variable types that are the void we already talked about, which means nothing. There is a car, which is a character. So it's a 8-bit sign. Believe it or not, characters are signed. Signed value. There is a byte, which is actually a pound defined earlier, which is an unsigned car. Okay, and these are things that don't mean anything down at the binary machine language. This is all at the C code level. So the compiler looks at this and it says, oh, if I use a car, and so you would think it's 8 bits is equal to the 8 minus 1 is equal to, or 0 to inclusive. So that would be 0 to 255. But in a car, it's actually equal to negative 127
or 127
to positive 128. So if you get to 127 and you add 1, now you've got negative 1. Whereas a byte, it's or an unsigned car, you've told the compiler, oh, this is this 8-bit thing called a car, but we're treating it unsigned. And so now it knows to do the math differently with it. That's what's going on there. You also have to be careful because when you use an unsigned, there's no such thing as a negative number. So you could really screw yourself up. Then there's an int. Now all these things are potentially machine dependent. An int on the Arduino is 16 bits signed. And then of course an unsigned int is a 16-bit unsigned integer. There's also there's a uint underscore 16t, I think, which is basically the same thing. Probably you don't care. There is a long, which is 32 bits, and an unsigned long, which is unsigned. You want to be careful with these because the Arduino is an 8-bit machine. And now when you start saying I'm going to use 16 bits and 32 bits, now the compiler is playing games where it's taking 4 different registers and it's moving things back and forth between the registers and doing all the math one at a time. And now what you would think should be fairly quickly run starts getting really, really slow because you have to play all these games to make things happen. Also, C lets you do division and multiplication. 3 divided by 2 is actually equal to 1. 3 divided by 2.0 is equal to 1.5. Because if you just do that, it assumes they're both ints.
It rounds off the number.
It does not round off.
Well,
It truncates. There's a
Yeah.
difference. There's a big difference.
Yeah, because rounding can go up or down.
Well, yeah,
Truncating.
truncating would be better.
And you can do the
It just truncates.
You can do the mod of the thing to get the
Right, so, yeah, and so you gotta be careful. So you've got an int, and then you've got a float, is a 16-bit floating point.
And that will really drive the Arduino nuts.
because now you're using floating point math, and I'm not going to go into what that is, Vice, but well, I'll do a quick bit. You've got 16 bits, and you store, let's say 1.57. You would have, I think there's a sign bit, and then there's the mantissa, I think it's called. So it would be 1, 5, 7, 1, 2. Actually, I'd have to turn that into binary. So whatever the binary representation of 157 is, would be here, and then there's some number of bits here that are times 10 to the watt power. In this case, 0 power. So now you want to do math in this, you've got a bit aligned and take this one and say, oh, this is that, and you've got to shift the bits this way and that way to do what you want. And works great. It's a great way to do things. But when your machine doesn't have it built into it inherently, there's a lot of gyrations you got to do. As soon as you say, I'm going to divide or multiply a float, things got complicated. Things slow down. Maybe you don't care. But when you start seeing things, you're like, God, that really isn't doing what I think it ought to do. Sometimes you got to take a look, right?
Yeah.
So, things to think about.
How come my Uno can't mine bitcoins?
It can mine 1 Bitcoin per 20 years.
Yeah.
And even that's a stretch, I think. So,
Ethereum now.
although a friend of mine can actually run a Minecraft server on that. He was going through a little fad for a
He
while.
ran a Minecraft server in Arduino.
I've seen him run a Minecraft server on an AT Tiny 44A.
There was one type of block.
No, it's really simple. It's a very small.
That's cruel, unusual punishment to the Arduino.
No, what's really cool is he has these videos, right? You can go in, you connect up to it, and your little guy walks in and it throws a switch, and when he throws the switch, a light comes on. He's actually diddling real hardware. When you throw a switch in the game, you're turning a light on or off or making something happen.
Well, they have logic switches and stuff. built
Yeah,
in the
they
game.
do.
It's
And-
crazy.
Well, and somebody had a mod to patch it into their IoT system, so they would flip a switch of the game in there.
No, this Charles has been doing this since I've known him, so for 7 years. He doesn't do it anymore. He's off on different tangents, but
Sure.
it's like he was doing it all the time for a while. It was really it's like, damn, that is stupid, but basically cool. And that is so it's so meta, right? You're walking.
Right.
I'm gonna walk in and throw this switch, and when you throw the switch, oh look, the
Well,
lights
the guy
go.
that built the computer in Minecraft, like he built like
Yeah,
hurts my brain.
yeah, but to run Minecraft on this, just a completely stripped down server. All it did was
Yeah.
handle the I/O. It can handle like 2 or 3 people going in at a time, and it's like, oh, damn, Charles, that is
I
really
just never gotten into the game thing.
it's a fun game.
It's
spent
just
way
it's
too many hours
Legos. You build
Yeah.
stuff.
That
I mean, it does more than that, but
I love the chuckle that most people don't know what's going on under the hood on a Legos Mindstorm. The only National Instrument knows for sure.
in 1998, I accepted my first job in the real world as an engineer out here. And I still had a month of graduate school left, I think. And I got a call from Lego. Do you want to come work for us? We need an electronics engineer.
Where were you at the time? Out in
Southern
California?
Illinois.
Yeah, out in Illinois? How did they find you?
I put out resumes to all over the place.
Did a broadcast, huh?
Well, you know what? I interviewed with Intel for their Xeon
series.
Xeon series team.
Try and promote it.
I interviewed with IBM
Yeah.
up in Fishkill, New York on.
It's a good thing you didn't do that.
Well, it was reverse engineering of ICs. I interviewed with HP out in Colorado, Symbios Logic out in Colorado. I interviewed with Microsoft for the Xbox team. All these things that were just coming out. And I was asking that. Well, I asked
Where
the
did
guys.
you go to school and graduate?
Southern Illinois University in Carbondale.
On Carbondale,
So
University of Illinois.
no, Southern Illinois University.
Oh, Southern Illinois.
But anyway, I was like asking Lego. I was like, "What the hell do you need a electronics engineer for?" Well, we can't tell you, but it'd be really cool. I was like, "Man, I really want to go."
Top secret at the time.
Patents are running out. We need something.
I was like, I'm really interested, but I already accepted this job, and I feel bad about, basically reneging.
Hey, I was going to go to work for Apple. Stupid me. The government told me to stay here. They begged me to stay here. That's stupid. I listened to them.
So anyway, I guess the short story is I could have been on the Mindstorm team. Maybe with
I
someone
wonder
else.
how they ever found National Instruments. Oh, somebody's
my-
trying to
It's
leave
my
you.
mom.
Of course.
Hey, Mom. I'm teaching a class. Can you call me back at 9? Bye.
Hi, Mom.
All right. So where were we?
Basic C structures, you did the integers, the variables, all that
So
stuff.
what we're gonna do is a real quick one. I'm gonna make one. It's called int add, and an integer you would add to ints. Sorry, I'm my capital letters. Int a comma int b. This is how you would do and in here you would have return a plus b. So return basically says terminate the set of instructions inside this function and hand back the value inside. And then up here in loop, for instance, somewhere I would say add x comma y. And up here at the very beginning, I've defined int x and int y. So before you use a variable, you have to define it. Usually on the Arduino, this all happens up above setup. So your defines, your declarations of variables, that all happens way up above setup. And then you use it inside. And so now when it gets to this line, it's got some number of lines. I've got some number of lines. When it comes here, the instruction pointer now jumps to here, and it hands these two in order. X goes to A and Y goes to B. And then it goes to there. And then the sum here you would say Z equals add XY. So the sum comes out, it's an int, and goes into Z. That makes as much sense as mud and spaghetti can make by looking at it. That's what happens. The upshot is if you do something more than once, you can write this little thing and then you can say add XY instead of doing this series of machinations that you would have been doing earlier. The next thing I'm going to tell you in code is anytime and every time you declare a variable, also initialize it. Most compilers will initialize to 0, but it is not
guaranteed.
It is not guaranteed. It is not a part of the language that says that it has to. It could initialize it to anything. It could pick up just a piece of memory that's already been used before and has some random bits in it. Most modern compilers are nice and will set it to 0, but don't count on it.
Only one way to be sure.
It's only one way to be sure. The next thing I'm going to tell you is, for your own sake of mind, comment the hell out of everything. I'm one of the few people that has ever been told by a computer science instructor, maybe you comment too much. You come back to this piece of code in 1 month, you won't remember what you were doing.
He's right.
In C, it is
Yeah.
That's the end, yeah.
and is that the end?
Yeah.
It's been a while. I don't
That
use.
star and then star,
And
star,
then-
star, and then the other right.
Yeah.
Back. Yeah.
Nope.
The other way.
Yeah.
There you go.
Anything in between these is a comment. For a single line comment, you can use C++, which is slice slice.
Yep.
Anything after a slice slice is a comment. So please do yourself a favor. Comment the hell out of everything.
Yeah, and if you think this is obvious enough and I'll remember, you won't remember.
Exactly.
You will
Write
not.
it down.
It may be obvious enough to read, but if there's one little thing that you need to remember that's special, you won't remember.
Another cool king thing to do is teach them Hungarian. That was a Microsoft idea.
No, I keep things simple.
All right.
People used to get all carried away and they would put as much code and meaning into a single line as they could.
Obfuscated C contest.
Yeah, it is. And
Yeah.
in the bad old days of the very first compilers up until the early 90s, maybe mid 90s, you could put your code together in a way that would come out much better optimized than what the compiler could do.
Mhm.
The modern optimizing compilers are very good. You are only doing yourself a disservice writing stupid code like that. It's much better to write A plus B equals C and then, write 5 lines of code that you can follow. I did this, and then I did that, and then I did this. Comment the hell out of them, see what you can do. The optimizing compiler will look at it and say, oh, all this is the same as just doing this, and I can do it in 3-bit moves.
Yeah.
And it's done. So, we'll go to the first homework. I'm going to bet. So the first homework 1A, was what? It was the blink of light, right?
Mhm. Half second on, half second off.
Half second on. So an LED does this. It looks like 0.55, but that's 0.5 seconds. Okay. So the most obvious thing you can do is you can set up you can say pin mode, choose your pin. What pin did you choose?
13 because it was the built-in one.
13, comma, output. That's the end of setup. Oh, no, you have to, no, it's output, that's fine. And then in loop, the brute force is delay 500. Digital write. $13, comma, high. Delay 500. Digital write. $13, comma, low. I'm willing to bet that's what you did. And lo and behold, if you turn it on, my machine went to sleep because it's not my machine. Thank you, machine. Come on. I see a little bit of light. There we go. should have plugged it in. So here's the brute force. This code is exactly that. I might leave it on here for the rest of the night. So there it is. I'm using pin 3 on mine.
Oops.
And as soon as I come over here and say, where's my mouse? Load it onto the board. Should see just that one start to blink. Should see.
Yeah, it takes a minute.
Yeah, the little progress bar.
Yeah, because there we go. And it didn't like it for some reason.
The kind of interesting thing about the boards we have is that pin 13 is the onboard LED, but there's still an external pin 13, so you can make both the onboard and an external blink.
Right.
I assume that if pin 13 was used for internal, that it wouldn't be available external as well, but it is.
I haven't set my.
You never limited design. You assume everybody wants to go everywhere.
Yeah,
There we go.
but it's nice that they did that. And
So now here I have a half a second blink. That's exactly that code. That is the easiest thing you could have done. Now here is the downside of this code. What if you want to do something else while you're blinking that LED?
those delays block it.
Those delays are blocking delays. Those delays, your machine, your little Arduino cannot do a damn thing while that's going on. So it will service interrupts though, which is a more advanced topic that we'll talk about. But this is the most obvious, this is the hello world for microcontrollers. Hello world, if you've never done software, is
Yeah, the
you sort
basic.
of print hello world to the screen. That's the first program you ever do to show, oh, something does something. So let's go take a look at,
Yeah, I did see an example on how to do it without delays, and I assume it used interrupts, but didn't.
no, there's actually two ways. There's actually another way to do it. What's this one? Toggle with a mask. Okay, so this one I did something a little different. So now we're going to start talking. This is very important for microcontrollers, is bit masks. So I'm going to define a variable up here. Point this back up to the screen. I need a cameraman, maybe.
2 cameras.
Bring it over here. Yeah, that's good. All right. So the first thing I'm going to do is I'm going to define a variable car. Let me do it all lowercase like I should. Temp equals 0. Okay. And now down here in loop, I'm going to delay my 500 milliseconds. And then I'm going to say temp is equal to temp exclusive ORed with 0x01. And then I'm going to do a digital write. Temp. All right. Let's talk about bit logic. So you can, first thing, if you do a digital write, a non-zero number, it doesn't matter what the number is. If it is not 0, that's high. It will turn it on. If you put a 5 in there, a 10 in there, a 15, a -3, a -27, it will turn that LED on. So if you're thinking that you're going to go through and add some numbers and do some fun things, it's not going to work the way you think it's going to work on that pin because you're doing a single pin. If you write exactly a 0 to it, I don't know what will happen if you try to throw a float in there. Even if the float's 0, I don't know what it'll do. It may choke on it, it may work. Who knows? So let's talk about, we'll erase our machine here for a second. And let's talk about digital logic. And so I'm going to have a letter X, a variable Y, a variable X, and a variable Z. And the first thing we'll talk about is AND. If X and Y are true, Z is true. There is whole mathematics written around logic. And it follows logic, like logical arguments. So an AND, 0, 0 gives a 0, 0, 1 gives a 0, 1, 0 gives a 0, 1, 1 gives a 1. This and that have to be true for this to happen. To do a bitwise AND, you would say, I'll do temp. I'll say temp and ampersand the bit mask that I want to do. So we'll talk about a bit mask. 0x01, the 0x signifies this is hexadecimal. So hexadecimal, 0, 0, 16 bits, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0. 1, 0, 1, 0, that's 10 by the way, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. This is 8 bits, so I've given you the first 4 bits. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, now let's see, in decimal, binary, hex, 9, 10, 11, 12, 13, 14, 15. It'd be easier if I just do that, probably. In hexadecimal, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F.
I remember that from computer science.
So when I say temp and 0x01, whatever is in temp, 1, 2, 3, 4, 5, 6, 7, 8 bits, could be anything, and with 0, 0, 0, 0, 0, 0, 1, that answer is 0, 0, 0, 0, 0, 0, 0, whatever that x is. That's what that bit mask does. So the next thing we'll look at is OR. 0, 0. This or this is a true, then this is true. So if it's 0, 1, this or this, yeah, true. This or this, true. This or this, true. Notice it's the opposite of an AND. Well, actually, no, it's not. It's almost the opposite of an AND. The next one is, let's see, AND OR. Let's see, an OR is temp. That is a pipe. That is the one right above your enter key. Shift that. That's a pipe. No, it's a pipe.
I know
It's
the
a
one,
shift
the one
shift-
over the backslash.
Shift backslash.
Yeah.
That is a pipe, that is OR. So temp OR 0x00, I'm sorry, 0x01. So if we'll do that one, we've got x, 1, 2, 3, 4, 5, 6, 7, 8, ORed with 0, 0, 0, 0, 1. What you're going to get out of this is x, 1. You don't know what any of those are, but you know that one's going to be a 1. These things are important, these ands and ors and exclusive ors, when you're setting, especially when you're setting up your chip at the beginning. You're going out and you're setting and clearing individual bits and registers. Because in our control scheme over here, and we talked about, we got your main core doing stuff. There are registers out there that tell it how to do those things and set up different pieces of hardware to do different things. So we'll be going, you'll look at your data sheet and you'll say, oh, if I want to do this, that means I need to set these bits a certain way. And then you'll go set those bits that way. An exclusive OR is a caret. 0, 0, 0, 1, 1, 0, 1, 1 is this and not that. So, or another way to think of it's one of them but not both. So this 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. This but not that. Or this or not that. I can have one or the other but not both. Exclusive OR. So
To exclude.
So now, when we temp this, now it makes a difference because if this is a 0, then that's a 1. But if that's a 1, that's a 0. Which is what I'm doing here. Instead of having to do this twice, I told it to do it just once. I simplified my code a little bit. I obfuscated a little bit, but I made things a little simpler, and I did it to introduce the idea of a bit mask because it's a very important concept. So up here, XOR, and then there's a NAND and a NOR, which are the inverse. So if I say NAND,
I guess that's not good.
dead soldier. NAND, NOR, that's 1, 1, 1, 0, 1, 0, 0, 0. It's the opposite function. Not and, not or. That's effectively an inverter, which is the not function, where we just go down to 2, 0, and 1. The answer is 1 and 0. This is signified by a tilde. So if you see a tilde, something that says invert whatever it is. So I couldn't just say invert temp though, because then it would be all 0. I guess I could have. I could have just said invert temp and that would have worked too.
Well, and I think the tilde is, well, at least I do a lot in PHP. The tilde is a bitwise not, so it would turn a 0 to a -1. If you start with 1, I think it'll turn it to a 0, but then you do it again and it turns into a -1 or something like
No,
that.
you start out with, you'd start out with 0, 0, 0.
Yeah.
So temp is equal to 0, I said that. And now tilde temp would give me 1, 1, 1, 1, 1, 1, 1, 1. But then to tilde it again, it goes back to 0.
Yeah, this is something different with PHP. It does something.
Yeah, so this is bitwise.
Yeah.
PHP, it probably says, oh, it's a -1, which is actually represented by a 2's complement, which actually is that, so, and I don't know what it's doing.
Yeah, it'll toggle between a 0 and a -1 if you do that. Also, it looks like an Arduino you can do the...
Well, this is -1.
Yeah, okay, yeah.
This is
Yeah,
-1.
Yeah, it's
and
one
it-
back
and
from
it-
all zeros.
Right, because it's a they don't, it's not a sign bit and the number, it is a 2's complement. And you do a 2's complement because it works for subtraction. You take the it's an easy function to do the 2's complement. It just bang, it happens.
Right.
And then you do the addition and it's the same as a subtraction, so.
And it,
There's also a 9's complement. That's how you add to subtract a number in decimal.
gotcha. It also looks like an Arduino you can do the exclamation mark to do the not.
Okay, so,
Or at least with the high-low, it works. I don't know what values it actually gives
okay,
you, but...
so an exclamation point is a logical function, not a bit function.
Gotcha.
So we're there, let's talk about it a minute. So, eventually you're gonna come up to an if. If something, then this. So, we'll say X. This is the most common mistake I make when I'm doing logical comparisons. X equals 7
Nope.
is always true.
Yeah.
Because when I did it, and it's true, I did it.
Mm-hmm.
What you want is X equal 7.
Yeah, it's a comment.
This is the logic. This says,
Even engineers make those.
this is, does X equal 7?
Ask the
Yes or
question.
no? This is asking the question. This is saying X equals 7. It is assigning X to be equal to 7. And the result of that operation is always true. If over here I said X equals 6, when I say if I say X equals 7, now X equals 7. But if I say X equals 7, it says, false, and X is still equal to 6. Is that as clear as mud? So, if X equals 7 is true, we usually leave that part out, then do this. Otherwise, it just skips to the end and starts down here. The next question is, greater than or equal, less than or equal,
Not equal.
not equal. That's where you see that. There's also,
Double brackets for comparison, greater than, equal than. So
well,
if X, left bracket, right bracket is equal to exactly 7. Oh,
I
you
have-
just said that.
no, yeah. we
Well,
don't
there's
use that
another
one.
way of doing it
It's
too.
equal. I've never seen that used. I didn't bother to bring my Kernighan and Ritchie book. They're the guys who wrote
Problem
the
with
C
me
language.
is, I'm at this point so polymorphic in language, it's a
Yeah.
multi-stack. What you're doing here, and what you do in Visual Basic, what you do in PHP and 5 other different languages, it varies a little.
There's
It's supposed to be logically the same, but doesn't
Yeah.
always get expressed that way.
There's definitely a few that'll let you do less than, greater than for not equal to.
Well, yeah,
Things like that.
the double signs are used that in Visual Basic for comparing stuff all the time. They don't use the double equals.
I'm trying to remember. There is in C the double and the double or,
That's
Yeah.
true.
and those are logical.
Most
But I don't remember how you use them.
most languages I use on a regular basis will use those for the comparison. So double pipe for or and double ampersand for and.
Yeah.
The single does
The
it.
single is a bitwise. So
Okay.
one's bitwise. The single.
Gotcha, and the other one's logical.
The other one's logical,
Yeah.
but I can't think. I can't think of a time when
It's
I've done
rarely
that.
used.
It's rare.
Just in if statements all the time.
Why would I in an if statement say this or this? I guess yeah, but no. I would
All
do-
the time.
No, well, no. I
Not-
would be doing. It would be a bitwise, not a logical.
Not with the
It's
double.
not asking a question.
What you can do,
I just-
well, okay, here's what it is. X equals 7 or X equal 9.
Yeah.
There it is.
Well, double
Right.
equals.
If. No, yeah, you're right, double equals.
Yeah.
If either of those are true, then we'll do
Yeah.
it.
Right.
And then the opposite of that is and.
Yeah, the double ampersand.
I have a hard time doing ampersands. I
And
usually
then-
just do that.
Yeah, and you can string those together.
And PHP being so loosely typed, you have a triple equals for is the same type and the same value, or exclamation mark double
So to
equals,
use a
or does
triple-
not equals.
So you're comparing the variable as well as the value, the type.
Yes,
Type can
because PHP will
have to have the same.
will
type.
convert types left and right.
Unfortunately, I left off PHP around 4.5, and then I did a little bit of 5,
Yeah.
with major mess between 4 and 5.
But we're sticking with Arduino and the
started with
Arduino
3.
environment. So. So we've gone through that. So I can show you this piece of code right here is exactly what I wrote. It's temp equals temp exclusive or 1. And bring that in and zoom it in so everybody in the world can see that.
You know what I'm going to do with you guys? I'm going to empty all my data books.
So that's exactly what I wrote. And when I tell it to go, you're going to see that the little blinky light, if I don't get any errors, this is what I get for running on a battery because it's gone into super power efficient mode. I should plug it in so I can.
There's plenty of plugs back where he was.
Yeah.
God, this is taking forever. Oh, there it goes. Maybe. One little bit more. God.
Oh, there it goes. See the,
Blink. So you see it blink once and it's doing the exact same thing.
mhm.
I saved a line of code.
Yeah.
Big deal, right? Whoop-de-doo. So now we're going to go to the next one. I'm actually going to go here and then we'll come back to this. So I want to show you the downside of doing this. Sorry, while you're pulling that up. Okay, so here I've done a couple of things all at once, and I'm going to plug this in while he's off doing whatever, so that maybe my junk will run a little bit faster. It'll certainly get a little brighter. All right, so what I'm doing is the first thing I've done is let the people at home see this, I guess, for a little bit. I'll write it up here on the board, but here I've actually done a define of an out pin and a define of an in pin, which we're not using the in pin on this one. And I've got a couple of things going on that doesn't need to be there. So I've pound defined Out pin is 3. Pound define. In pin is pin 2. Then I've said car temp equals 0. My setup, I have done a pin mode, in pin is an input, which I'm not using right now. Pin mode, out pin, output. And then I've done 4 more pin modes, 4 more outputs, pin mode 8, 9, 10, and 11.
So you're video capturing all this for later, huh?
Yeah, I put it up on my
Oh.
YouTube channel and then share it out.
I
to
gotta
the
run
world.
for now, I'll look at it later, yeah. I'm just curious what you're up to. I mean, I've been doing this sort of stuff for 30 years.
I am just teaching the very basics for people who want to be makers.
I know. Well, you gotta start, yeah.
And you can branch from here, and I'm open for questions if people want to ask questions.
I always tell people about Arjuna, the reason it's so popular is he's the number one reason it works is the very thing he has in the top, the define.
Mm-hmm.
The whole game plan in Arjuna was to teach the Arjuna English, essentially, and they did it by the define statement, and it works. It's great. It's done miracles.
So-
I'll catch you guys later.
Cool. Nice to
All
meet you.
right.
So now down here in loop, I've done exactly the same thing I did before. My mouse moved way over there. But I've added some stuff. Oh, there it is. Up here I also have a byte. Count. Volatile is another keyword. Volatile indicates to the compiler that that variable could have changed. Now, for this, it's useless. But so if I come over here and I say int I equals 13, and then I come down here and I say I plus 3, z equals I plus 3, the compiler, what's going to happen is the computer, the Arduino, the processor, is going to come here and it's just going to say, oh, I'm going to put a 13 in there, and it's going to say z equals 16. By saying that it's volatile, it's saying that something else could have changed that. I said it's 13 there, but by the time I get down to here, it might not be 13 anymore. Something else may have changed that number. Something else off over here somewhere has the ability to change the value of I. And so what that says is when I get to here, it reevaluates I. So the compiler itself, when it goes through, if I just set at the very top I equals 13 and I never change it, it's just going to use 13, 13, 13 until it sees something that says, oh, I'm changing I. Now I need to reevaluate I and go through. But if I say it's volatile, it says, I don't really know what I is. When I get to this point where I use I, I'm going to reevaluate what I is. I'm going to go actually read it from memory and put it in here instead of just using a marker. Well, this doesn't make sense right now.
No, because,
I get it.
because that you seem to be talking about a variable, not a constant. So that's
If I just say this,
yeah.
until I say I equals something else,
Right.
it's a constant.
But wouldn't volatile be indicating that at some point something does say I equals something else, which would be the
No.
same as not saying volatile?
No.
I think I'm confused
Okay.
as to where it might change it, but
Okay.
it wouldn't be a variable.
I have a process. I say, at the very beginning, I say int I equals 0. And then I say I equals 5 plus 7. You know, really x plus y, and somewhere along x and y have been defined, right? And so that evaluates to now I is equal to 12, right? I equals 12. And so, but over here, up here, so let's say right here I say z equals I plus 5. Well, here z is going to evaluate to 5, clearly. But the system knows that it was equal to 0 and I haven't done anything to it to change it. So I do not
Need to reevaluate.
I do not have to go out here to memory and say, give me I, and come back and put it in here. Remember we talked last time, once you get on the memory bus, you're taking time to go out and do stuff. Instead of,
Well, where would I be stored then, if not the memory bus?
it is stored in the memory, but the compiler is playing games, right?
Okay.
The compiler is an optimizing compiler,
Gotcha.
and it says, why should I get on the bus and waste a clock tick, 2 or 10 or whatever it takes, when I know this hasn't changed, right?
So if you don't designate it volatile, does it treat it more like a define?
So, until you change it.
Right.
Now the compiler says, oh, something changed, and we'll read that in as a temporary variable, and we'll hold it however long we need to hold it, and whatever else. Because a lot of this kind of stuff, you don't really need, these are constants, right? This is all done in the compiler and doesn't actually get done on the chip. The optimizer
Okay.
will come through and optimize all this out and say, that's 13.
Okay.
Or, I'm sorry, that's 12. We don't need to do anything with that.
Right,
Why
right.
waste clock ticks making 12,
Right.
right?
Right. When you can pre-compile it, you can pre-process it in the compiler.
Now, if I have some other process over
Okay.
here, and it says I equals 6, and it could happen at any time, we don't know,
Then volatile.
that's a volatile thing, because it's going to feed in here and change this value. I could say int equals 0, and right away this says, nope, I equals 6. And then when I get to here, so now it's a volatile int.
So that means check it every time it's used.
That means don't do it in the compiler.
Right.
That means go out there, grab that piece of memory, whatever that we've decided is I, and throw it in there and use it.
And Arduino can do the multi-process.
We're going to get there.
Okay.
We're going to get there tonight.
Yeah, I'm used to things being sandboxed so that other processes aren't affecting your process. I mean, if you're going out to a database, sure, but then everything's sharing that, you know.
Okay, so then what I did down here, in mine, I'm saying this because the people who can see my screen, who can't right now, they saw that byte is labeled volatile.
Sure.
And that's because I was bouncing back and forth between these, what did I say, 7 different pieces of code that I wrote the other night to introduce you all to these different things.
Sure.
So, did that. Okay, and loop, I did the same thing. I said delay 500, twiddle temp equal equal temp XOR 0x01. Shorthand. I didn't use it because I was trying to be explicit. If I say temp equals temp XOR 0x01, I can instead write this, temp equal XOR equal 0x01. Basically, it says temp, it is equal to itself XORed with that. and you can do, there's also an and equal, an or equal,
Plus equal.
no,
No, not in our.
plus plus.
No, plus plus to increment, plus equal another value.
Oh, yeah, to add.
Yeah.
There's plus equal, minus
Right,
equal.
Right.
I don't think there's a divide and multiply equal. There might be, I've never used it.
Yeah, I don't know. think
I
can
almost
teach
never
more.
use these because I'd rather write it out and be explicit. I will do the XOR, ampersand, and or equal. Those ones are second nature. Then there is count plus plus, and there is plus plus count.
Yep.
The difference in these is when they're evaluated. If I say, let's say count equals 0, now count is equal to, at the completion of this, count equals 1, and now at the beginning of it, count equals 2. So what this happens is if I say temp equals 5 plus count plus plus, here count equals 0. When I get done with this line, temp is equal to 5 and count is equal to 1. Because count plus plus happens after you use count. But if here I say temp equals 5 plus count, which is certainly confusing, then at the end, so count was equal to 1. Now temp is equal to 7 and count is equal to 2.
That makes sense. So basically, the 5 plus count is going to say 5 plus count, evaluate that, put that in a temp, and then increment count. It's going to plus is plus 1, basically.
Plus plus is a increment.
Whereas the second one, it's going to do the plus first, then add it to 5. It's just the order in which it does it. Either it takes the 5 plus count and then increments count, or it does 5
Plus, this is an increment. It's an instruction to increment.
It's just a plus 1.
There's a
But
minus
it's showing
minus is decrement. So plus is add 1, minus is subtract 1. But if I say count plus, you evaluate count, then you do the increment. If I say plus count, first I do the increment, then I do the evaluate.
There's times when
So
that
so
makes sense.
so this here is what I'm saying. If I start off with count equals 0, if I say temp equals 5 plus count plus, there's every reason to believe that you thought that the answers to this should be 6. Except that the increment operator happened after the evaluation. So the computer comes in and says temp is equal to 5 plus count, which now needs to be incremented. So the answer of temp is equal to 5 plus 0 incremented is temp is equal to 5, and count is now equal to 1 in the next line after this.
Yeah. Generally, people don't.
But if I say 5 plus incremented count, now that count is equal to 1, I will get temp is equal to 7 because I did the increment before I did the evaluate for the expression, and count will be equal to 2.
Yeah, generally, people won't do a plus in the middle of a.
Generally you don't do a count plus in the middle. Somewhere you'll be off somewhere and you'll say, oh, count plus. And everybody just thinks, oh, count plus, that increments it. But it can make a difference.
Yeah.
This is a subtle case. Like you said, most people won't do this. But there have been 1 or 2 other cases where I've done this, and it took me a while to figure out why the hell am I getting the right answer. Light bulb moment. It needs to happen in this order. Because remember what I said, the computer's going to do exactly what you tell it to do, even if that's not what you meant for it to do.
Yep.
Because, you know, this is actually fairly common. Oh, every time I go through this loop, I need to do something and I need to increment count. I mean, that's a while loop, right?
Yeah, that's like that VBasic that you wrote from the spreadsheet where it
In fact,
still reads the data and then
Yeah.
it moves it down a line.
Yeah.
in fact, in very fact, this is a for loop, x equals 0, x less than 13, x plus plus. The first time through this loop, x is equal to 0. The first time through that loop, x is equal to 1. That's an important difference.
You sure?
Yes. I am absolutely sure.
It's interesting because I would assume it would start with the 0 and it wouldn't look at the third parameter until it
This gets done. No,
Until
this
the
gets
third
done
loop.
right off the bat.
Okay.
Right off the bat, that's done. You can write your own code, and if I'm wrong, I'll buy you a Coke.
So does that keep going as long as x is
Less
less
than
than 13?
13.
So
Yep.
once it hits 13, it would stop?
Mhm.
So what you'll do is you have a for. It's called a for loop. And so in here you might want to z equals x plus 5, right? The first time through here, x plus plus, z is equal to 5, z equals 6, z equals 7, z equals 8, z equals 9. It's a nice way to increment things when you know you got to go. You don't have to do x plus plus. You can do x plus 7, right? So it'll make it through the loop twice. It'll go 0, 7, and then it's going to be 14, and it's too big. I quit. I don't do anything more. Now, you can have any regular expression over here that fiddles the value of x. But usually, you won't write x plus 1, you'll write x plus plus.
Drives me nuts the languages that don't do plus plus and you do x equals x plus 1 and it's like that.
It's so painful. Yeah.
it's dumb because it's only like 3 extra characters, but it's dumb that it doesn't do it.
Well, no, that is an extra. That's an extra, for lack of a better word, semaphore that
Yeah.
your compiler has to understand,
Yeah.
and so that's one more layer of bullshit that you have to go through to do it.
But welcome
When
to the
Kernighan-
21st century.
When Kernighan and Ritchie wrote C in 1975, this was a huge jump forward, right? I mean, everybody was writing Fortran or assembly language before then. And, and this is nice because you still are at the level of the register, right? The whole reason, one of the things that's built into a lot of ALUs, the arithmetic logic unit, is an increment function. Where just bang, in one tick it can increment the whole thing and add 1.
Ink deck.
And ink deck. And this is a mapping to that functionality in it. There are some heavily typed languages that I've done where you can't even say x equals x plus 1. You have to, I mean, Eiffel is a language that is written to be, oh my God, I am object oriented. And you have to call a function add
Sure.
to add two numbers together. And it is severe. It was made originally to replace COBOL, which is the big banking languages, right? So it had to be type,
Sure.
It had all these type restrictions and everything else. And they overcame them by going completely over the wall with object orient. And it was, there was a math class, and part of the math class was an add function, a divide function, a multiply function. But like COBOL, it stored thirds. In C, in almost every language, 1 divided by 3.0 is equal to 0.3333, however far it can go. And so if I say x equals 1 divided by 3.0, and now if I say 3y equals 3 times x, notice I used an asterisk, I call it a splat, 3 splat x. What's my answer? Y equals 0.999.
Right.
It's not gonna be one.
COBOL and Eiffel will report that as a 1. Because they keep the flag. They say this, you got this number by dividing by 3. This is actually 1/3. How they do that, I don't know. That's down in some sort of,
Yeah.
down deep in the guts, somehow they keep track of that. Okay, so I said delay 500, and then I said delay 100, count plus plus, because what I want to do is have count go up, and then I wrote a function called, what did I call it? Display count. I just did that. I think I actually sent count. And now I had a function called display count. This is how I write. I write capital block letters. These are lowercase, that's uppercase. Sometimes I actually do them in lowercase just to be clear, but. So here I have a function called void. It doesn't return anything. Display count, a volatile byte count. Actually, I probably just said byte count. So that says that what's coming in should be a byte. And it doesn't have to be named count. It could be byte value. But when I call it up here with the variable count, this variable takes it. I don't have to use the same name in both, because I do all my operations here. And here I said digital write pin 8, comma, masking, value, and 0x01, 9, value, and 0x02. Remember that that's 0010. 10, value, and 0x04. That's 0, that's 1, that's 2, that's 4, that's 8. 11, value, 0x08. Return.
So you got all fancy with your count display.
What I'm doing is I'm taking the 16 values that are the bottom the 4 least significant bits of count, and I'm putting them out on these LEDs over here. So what I think I want to do is I want to wait a half a second between the times that I blink the big light, but I only want to wait 1/10 of a second between my counts. So ideally what I really want to see is blink, 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 right? While the counts are sitting here merrily counting away. Blink, blink, blink. But instead, what we'll see can't hurt anything. Whatever gets there. There. Now we see my lights merrily counting along. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 0. Notice they're going basically the same rate as that guy. If you were to sit down and get really clever with your timing, you'd find out that that's 600 milliseconds high and 600 milliseconds low. That's a 1.2 hertz, not a 1 hertz. So this is what we were talking about before. The first gut thing that you want to do is just do a delay. But now while you're doing the delay, your machine is dead while it's waiting for that delay to be done. It can't do a damn thing else. So, delay is useful, but dangerous. So, here's the first easy fix to this. There is an Arduino function, so I'm just going to point it out here. So I delay 100, and I do my count. I display my count. And then I have a new variable that I'm just calling a count test. Millis. Millis is a function that's included in the Arduino libraries that gives you the number of milliseconds since the program started. It's a big enough of a number, it's an unsigned long, it's good for like 54 days. So as long as you're not going to be running more than 50 days or so, it's great to do this. What I'm doing is I said, if I say count test is equal to the current millis minus this value timer that I just started at 0. I started at whatever the time was. So my first time millis minus timer is just a few. But if it's ever more than 500, which is 500 milliseconds, right? Then I toggle that bit, and timer is now equal to the current millis. And now I wait another 500. Now, see that I'm getting what I wanted to do before. Mm-hmm. So this loop is running. It's still delaying this 100 milliseconds every one of these. But now I'm doing this game here. I'm looking at that. Now I could do the same game for the count that I'm doing for here, and things would be running as fast as they could, and there'd be no delays at all. I'd be wasting the clock ticks going through,
Mm-hmm.
but
you could still do things while you're waiting to do things.
yes, yes, and that's the point, right?
Right,
I mean,
right.
we want to be able to.
Sure.
All right, so now let's go to. Let's see, we did homework 1A, and then the toggle with the mask. So the next one's the button light. So the button light is, okay, so here I've defined out pin as 3, in pin as 13. I've got this temporary variable called temp. And like I said up there, pin mode, in pin is input. Right? Now if I've got a whole bunch, I just change it once up here and I don't have to go find it. Out pin is an output. And so now I'm just going to loop through. So this was the second one we did, right? Which was, go ahead and load up there, pal.
You can do it.
It's much faster now. All right.
There you go.
So when I push the button, oh, I've got the pins wrong. In pin is in pin is 2. I changed things since I did this because I found out some stuff that I didn't realize. Save. And here's the beauty. I changed this in that one spot. I didn't have to go find it in the code. And if I did it all right, there. Now when I press it, it lights up. When I let off, it goes away. Notice I've got the tilde in front of there. Because the way I've got my switch wired, when I press it, it goes ground. So what it really sees, if I didn't have the tilde, it'd be on now, and when I pressed it, it would turn off. If you want me to show you that, I can show you that, but you want me to show you that?
I think we understand. You understand?
Look at she's the one that's got the question mark over floating over her head. So
the the tilde is the inverse.
yeah,
Okay. I get it. I just had to think about that for a minute.
Yeah. It's
yeah.
the
Tilde is a bitwise not.
Yeah.
So
versus the code example that I used the exclamation mark to do the logical not, but
Yeah.
same effect.
Yeah, either is correct. Now this one, this is the hard one, and now we're going to get into the idea of the volatile and why we have a volatile. So we're going to discuss interrupts. Now, what an interrupt is, I'll put this back up here to the board. There are a lot of interrupts available to play with. However, the function that I'm using on this one is only a pin change interrupt, and it's only available on a couple of pins. I think it's 2 and 3, which is why I put these on, moved these over to 2 and 3 after the fact. I didn't realize that to start. So if we remember, we've got my instruction core doing instruction core things. And you will often hear an interrupt called an interrupt vector. Okay? So in my code, not my code, hardwired into the processor is a little table. A table is a vector, right? It's an array. And you have in your program space, you have, these are interrupt vectors. And this is number 0, 1, 2, to n, however many there are. And then right here is where void main starts. Okay? So when you very first start up your machine, there's an these are instruction pointers. All right, so your instruction pointer tells you where to go. It starts right there. It's 0, 0, 0, however many zeros. It says that's my first instruction. Which it's not really 0, it's really n plus 1. And when every time a tick happens and you do something, you increment this instruction pointer and it points to the next line, and then it points to the next line, and then it points to the next line. When you attach an interrupt, if interrupts are enabled, that interrupt, when the processor sees that happen, it immediately grabs hold of the instruction pointer and puts it up here into the vector table, where it's supposed to go. When you write an interrupt, an interrupt service routine for that. Let's say that was 3. Number 3, some code. What happens is when you've done this, down here, this is at line 7032, I don't know, of code, of assembly code. When you write this, the compiler knows that your first line of ISR 3 is at 7032, and it puts 7032 in here. So, this is convoluted, I understand. So, over here, I've got an input pin, and it just went 0 to 1. Pin change interrupt is enabled. I'm going to say it's not true. I'm lying. It's 3. I'm just going to say it's 3. I think it's actually 8, but I don't know. I'd have to go look. So this thing happens, and over here is a little piece of hardware that kind of says, "Oh, an interrupt happened," and it pirates this guy. So some guy in his floppy pirate hat and a patch on one eye, yar, comes in, grabs the interrupt pointer and says, "Go there!" And it goes there. And if you have an interrupt written at 7032, it says, "No, not here, go there." And then it runs the routine. And when it gets to the end and says, "Oh, it's done," it says, "Okay, now go back to where you were."
It interrupts.
You're basically forcing it to go to a different place in the code.
You're interrupting the code. You're interrupting
You're
it.
setting a condition saying when
So
this
it's
pin,
going to here, and then it's jumping down here, and then when it's done, it goes back to where it left off.
if the interrupt was triggered,
If the interrupt.
it interrupts.
Hey, I want... No, you don't! Okay, I'll do what you told me to do.
It's a petulant child.
Okay, Mom.
Yeah. It's not a pirate, it's a petulant child.
I'm explaining this to you because if this takes a long time to troubleshoot to figure out what the hell's going wrong. So I wrote these 7 pieces of code the other night that should have taken me 2 hours. It took me 45 minutes to debug this. Because I had this number wrong. What will happen on an Arduino anyway, I can't, on an Atmel microcontroller, if you haven't done this, then the program counter will go here, and then it 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 will fall back into void main, and it will start running the program over. So if you did not write this ISR, but you attached an interrupt, which means you turned the interrupts on, oh my god, it happened, hijack the thing, put it over here, and do nothing.
There's no...
So basically you go nop, 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 run. And so your code just keeps running over and over and over and over and over and over, and you're like, what the, this isn't what's supposed to be happening, what the hell's going on here?
Yep.
That's what's going on there. And it was because I had, in my ISR, I had put the wrong value in there. It turned out it was supposed to be all capitals, and the piece of example code that I was looking at on how they did it, they didn't capitalize it.
Mm.
So I had to go through and look through the data sheets and find out what's that called, and
Lesson learned.
go through and do it. And then it worked fine. And that involved using lots of print statements and using the serial capability of the Arduino that's built in, and doing it the old-fashioned way, print state.
Yep.
You're at point 1, you're at point 2, you're at point 3, you're at point 1 again. Huh? No. Well, maybe what about here? Point 6. Oh, you're at point 1, 2, 3, 4, 5, 6, and 1 again. Okay, well, I'm making it all the way through that. Well, what happens if I do over here? You're at point 1, point 2, you're at point 10, point 10, point 10, point 10, 10, 10, 10, 10, 10, 10, now you're back at 1 again. what the hell is causing
It
this?
does exactly what you tell it to do.
They
It was doing
have
exactly.
the signs at the work where it's like computer's only as smart as the operator.
So,
It's the GPS telling you to drive off the cliff.
when you're using interrupts, if you ever see this behavior, or that it's going to the wrong interrupt, if you have more than one, chances are you told it to go to the wrong place. Just saying. So,
And the slightly smart person might say, well, why doesn't the compiler tell you that there's no code there? And then the slightly smarter person might say, there might be a reason you might want to do that intentionally one day.
yeah. Well, you know, on the bright side, computers are designed to be extremely repeatable. So when something like this happens, most of the time, especially down a simple, very simple bare metal like this, it's going to be doing the exact same thing over and over and over and over and over. And as soon as you can kind of tease out what it is that's going on, oh, hey, it's restarting. Every time my interrupt, it looks like every time my interrupt should be firing, it's going back and rerunning the code. Hey, Google.
Yeah.
What's this mean? Oh, okay. Now I've got the right trap to go down. So, if you look on the Arduino site, and you look under interrupts, there's a function called attach interrupt. And you do this in setup. So in setup, you do a bunch of shit, and then you attach interrupt. Digital pin to interrupt. And I've got in pin up here, right? Pound define. In pin was 2, I think. In pin. And then, so this is which interrupt? And it's only external interrupts, which means it's only things from the outside world. All those little fun devices running around inside that we're going to play with, almost every one has its own interrupt capability. Those are internal interrupts as opposed to external interrupts. Here is the function. Counter. And then there's like 5 choices. I used rising. So on pin change interrupts, there's a choice of on the rising edge, there's the choice of falling edge, there's a choice of a transition to high, so it cares that it's been high, which is not the same as that, and there is a transition to low. So I think the 4 choices are rising, falling, high, and low. I chose rising. So what happens is setup happens, and then loop. And then down here I have counter. So anytime I see a rising edge, I fall into counter and I say count plus plus. And that's all I do. And over here I have volatile, byte, count equals 0. This is why I want a volatile. I don't know when somebody's going to push that button. Somebody pushes that button, I fall into this interrupt, I do this, count's changed its value. I'm over here doing nothing in my loop, but saying display count. Show me count, show me count, show me count, show me count. If I did not tell the compiler that this was volatile, it would never change.
And it's because the interrupt is acting almost like a second process, not so much a shared memory space of the same.
So here's the truth. Windows, all of these multitasking operating systems, up until recently you had a single core in your computer. What's going on in there is a timer, and it's doing what's called task switching. You start up a task, and you have a handler assigned to you, and in your time slot, you get 10 ticks that you're allowed to do some stuff. And then what happens is a timer interrupt fires, and it says, oh, we take away control from that task, and now we move the program counter over here to this other task that's running. And now that other task runs. And so you have to be very careful down at the machine level when you're writing the code for these things, that this task and that task aren't sharing the same memory.
Right.
Because if they are, one's going to start overwriting the other and everything's going to explode.
Right.
Even now, that's basically what happens. When you run Windows, there might be 14 cores, and each core might have 2 instruction pipelines. So it can run 2 sets of instructions at a time, 2 different programs at once, but you're running more than 2 programs on there at once. So there's actually an interrupt that's running
Right.
every microsecond, but you're running a thing at 3 gigahertz, right? So
Right.
3 gigahertz into a microsecond, that's 300,000 instructions per microsecond. A million times a second I can be switching, but my 10 programs can each be getting 300,000 instructions done
Right.
in that amount of time. So they're going to run slower than if they had full control, but it gives me the illusion that I'm running multiple things at once. And it's multitasking. I switch, round robin usually. Or you can have a priority. So this one gets 1, and then these 2 go, but then this one goes again, and then these other 3, and
Right.
so this one has a higher priority. And if you look in your task manager, you can right-click on a process and change its priority.
Yep.
That's what you're doing. You're giving it more processor slices.
Yeah.
So now if I run this piece of code,
Well, you're giving it more than things with a lower priority.
yes.
If you set everything to high, everything's going to get that same share, well, give or take.
Yeah. So the whole point, this was the extra credit, and the whole point of the extra credit was to bring in interrupts so that we could talk about these kind of things. So let's load him up.
I like roaming through here.
Oh, excuse me.
Figured out my dumb thing. Well, my LED wasn't.
Okay, so this should work. So if I press my button, so right now, I've never pressed my button, I've got no bounces. I just got 3 bounces. So it just told me that when it hit it, I got 3. Now the next time I press it, I should expect it to go to 4, but instead it went to 5. So I got 2 bounces that time. So now I expect it to go to 6, but instead it went to 7. So I got 2 bounces again. I got 2 bounces. I got a gob of bounces. I got exactly no bounces. I got exactly 1 tick that time. I got exactly 1 tick, but then I got 3. And I got a couple. My light comes on just like it's supposed to. But then when I let off of it, I see how many bounces it bounced. So what we're seeing there is what happened is when I did that, that light actually went on and came on multiple times, but it was so fast I couldn't see it.
Mm-hmm.
But imagine what's going on inside your processor when you're telling these things, right? This is the idea of debouncing your switches. You can do it externally like we talked about, or you can write code that does it here. And the way you can debounce it, we can go back to that timer function, the millisecond function that I did before, and you can have a variable in there that says, oh, you went high again, but it hasn't been 20 milliseconds, so I'm going to ignore it.
Mm-hmm.
From the first one. Oh, you went high again, but it hasn't been, so we're going to ignore it. The very first one that comes in, you get it, you set it, and then when it goes bang, 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 you just ignore things until after a certain amount of time. You do that off in the interrupt, and now it's not slowing down your code except for that one little time, that 5 instruction ticks that it takes to go. Now, what I've figured out in doing this and a bunch of troubleshooting, because in the next one I showed you I get fancy, as an introduction to the next things we'll talk about. It takes to get in the amount of time that it takes to get into that code was 24 times 256. It was 6,000 clock ticks to get into that code using the Arduino and all the it adds a lot of layers of crap on there. So that's just so you know, it isn't instantaneous like I made it out to be. It does take some time. There's overhead. Mm-hmm. When you jump into that interrupt, you can't just jump into that interrupt. All these variables you've been using, you need to take them and you need to store them somewhere. And so, because now you're going to go do other stuff and it will screw up all those variables. And those variables are actually the registers inside the ALU that you've been fiddling with. You know, mm-hmm. This plus that and this plus this other thing. And now if I go over here and do something else, those are going to be all screwed up. So I've got to push those onto the stack, is what it's called. And then I come over here and I do what I need to do. And when I'm done, I write that stuff to the right memory that I need to write it to. And now when I exit the interrupt, I've got to come over here and take all those variables that I stored and put them back and then set my instruction counter back where it was so that apparently nothing changed.
Right.
Nothing happened. Really, a whole bunch of stuff went on.
A little swapperoo.
A whole bunch of stuff went on in the background and made that happen. So
looks like on our boards, if they're fully compatible, we should have 6 interrupt pins.
yeah, so the Arduino Uno has 2, I think.
Yeah,
2, 3, 18, 19,
2 and 3 for the Uno.
Right, and then for the Do, the
Mega 2560.
yeah, there's an Arduino Do, an Arduino
Do
some.
has all digital pins are interruptible. Huh.
Yeah, Uno, Nano, Mini, and other 328 based are 2 and 3.
Mhm.
Mega 2560, Mega ADK have 6 pins. Yeah. Anyway, there's all.
So you're never going to have all your pins interruptible because then what are you going to be able to do with them? They're all going to be interrupts. You're not going to be able to do any outputs if you do all your pins. But what that does give you is flexibility.
Mm-hmm.
So you can more easily change.
Sure.
You know, instead of having to wire things onto this side of the chip, where I would have to run a wire all the way around to the other side, I can just choose one of these over here and change things around a little bit. It gives you flexibility in your chip. All right, so there's the extra credit homework, right, that I was talking about.
Mm-hmm.
And that's an introduction to interrupts. So now I'm going to get this ready. Let's see, so that we're ready. So we did the brute force, we did a toggle with a mask, we did the button light, we did the button count, we did a toggle with a count, and we did the toggle using the millis function. The last one is the toggle with an interrupt using the counter. And you see here, I'm down toggling bits in the code. This is an internal interrupt. Okay, so let's talk about, whoa, I about knocked my drink over. It's caffeine abuse. I loved it. I got this thing done on my neck yesterday, and one of the things they said is drink lots of caffeine. Today, I'm hooked.
Doctor said.
That's my usual state of being.
I have no trouble with caffeine anymore.
You know what? My son is on the, he's on ASD level 1, autism spectrum disorder or Asperger's, whatever it is. Level 1, that means relatively easy to deal with. But it's also ADHD type stuff. So,
See, one of the guys that caffeine calms him down.
I am.
Yeah.
I see a lot of me in my son, and I watch him and everybody going on about, oh my God, he's so hyper and whatever. I'm like, well, that's kind of what I was when I was a kid, right? People who know me, usually over Lent, I give up caffeine completely, and maybe a couple times a year I give it up for a week or two. Mm-hmm. I go hyper. I'm like all over the place, man. I start swilling the caffeine and I like calm down and focus.
A friend of ours says he can't drink coffee after like 5 o'clock, or else he can't go to sleep. And I drink a large coffee at 8 and go to bed at 9:30.
Yeah,
I'm
I've
fine.
gotten
Well, the medicine, Ritalin,
Yeah, it's a stimulant.
is a stimulant. And it's completely against what you would think. Somebody's all over the place and whatever.
Yeah.
I'm going to give them more stuff.
Yeah.
No.
It's more like it gets you in sync with something else.
It's
that's
a
out of sync.
probably a competitive inhibitor. Like it
I-
competes with the nerve and
Maybe. I kind of think of it as it's focusing. It gives you the energy to focus. Like maybe you don't have enough to be able to focus and brings it in. So yeah, I swill
Yeah.
2 or 3 of these a day, which is actually, I look it up. This was this a 20 ounce? This 20 ounce is a average cup of coffee. Mm-hmm. So somebody who's drinking 3 cups of coffee a day, if I drink 3 of these a day, the myth is, oh my God, you're drinking so much caffeine.
I gave up caffeine for like a month and a half, and it's just too hard. Everything has caffeine in it. Like if you go out somewhere, can't get iced tea, can't get
Nothing but water.
nothing but water. So
Or
it's just
Sprite.
like, I give
Sprite
up.
doesn't have caffeine.
Root beer. Most root beers.
Yeah, most beers don't. Unless you go over to Jailbreak where they have all the coffee flavor.
No, root beer is what I said. But yeah.
Oh,
Yeah, Barks is the only one I think that has.
orange soda. Orange soda.
Some of the orange sodas have.
Except, well,
Yeah,
only
but
Sunkissed.
Sunkissed.
Really? I
Yes,
didn't know that.
only Sunkissed. I think most of the
Crushes.
Other stuff.
So, all right. Here's what I want to talk about. Now that we've gotten off subject, clearly I'm not caffeinated enough. So, I changed it in one of those. Did I change it in that one? You'll see in this last one right here, display count. I changed it instead of doing the bit masking of all the different stuff. I just said port B equals count. Remember I was telling you that you can write directly to the port. You're writing directly to the registers. That's what I'm doing here. So on the Uno, port A is these analog, the ones that can be analog pins but are also digital I/O. That's port A. Pins 8 through 13 are port B, and I think pin 1 through 7 is port D or C. And you can go Google all that and find it out. Or you can sit down and look at the Arduino schematic and then compare that to the data sheet and figure it out yourself. It's a little harder, but... So instead of having to go digital write that bit, digital write that bit, digital write that bit, digital write that bit, I just said, write the whole register. Now it's one clock tick. Now it could be that those digital writes, the compiler looks at it and optimizes it all into a single write anyway. I don't know. But bring that up. So we've talked about, we have these 3 ports off here on the side, right? That are port A, port B, and port C. And these are I/O. Now, and these are devices with addresses out on the bus, right? So you remember last time we talked about there's an address bus that goes everywhere. That's the wrong way to draw that. There's an address bus and there's a data bus. And everybody has a hook off of each one, right? So when I write to port B, what I'm saying is, remember we went through the whole thing last time of, go take this piece of memory.
Alexa, stop.
Did I accidentally tell Alexis to do something? Oops.
Damn robots.
They do exactly what you tell them to do, even if it's not what you wanted.
Yeah.
So when we're out here writing to the ports, all these digital writes, we're saying, hey, go out here to the address, this address, and set this value. Now go out here to this address and set this other value. Now go out here to this address and put this data on. And remember, there's also like a read/write bar type thing that goes to, that's also global. So we've been down manipulating bits at the bit level, even though we didn't really realize it. The Uno, the ATmega 328, has 3 timers. I think that thing that you've got has 6. Maybe 5. I was reading up on them a little bit last night, just saying, oh, okay. Timer 0 is 8 bits. Timer 1, 16 bits. Timer 2, 8 bits.
This might have 6 timers, 2 8-bit, 4 16-bit.
Okay. I knew it was at least 5. So let's talk about what a timer is. A timer, we use the 8-bit one because that's easier, has a clock Okay, so remember that this represents it's edge triggered. So my clock source is here, and every rising edge, this increments automatically. That's all it does. Every time it sees a tick, 1, tick 2, tick 3, tick 4, tick 5. It is count, 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 count. It's as long as you've got a clock hooked up to it, it's doing it. It's doing it. So let's talk about the clock going into it. You've got the master oscillator, which on an Uno is running at 16 megahertz. I have what's called a prescaler. It is a multiplexer with 3 bits going into it, which means it has 8 positions. 1, 2, 3, 4, 5, 6, 7, 8. One is a no connect. So if I would have to look. If I choose the no connect, I think it's 0, 0, 0, no clock, my timer doesn't run. Each timer has its own prescaler, I believe. The next one is 1-to-1. That means I'm getting 16 megahertz out of the sky. You do the math, 16 megahertz, you're counting to 255 real quick. Then there's a 1-to-2, a 1-to-4. Is that right? No. It's 1-to-8, 1-to-16, 1-to-64, 1-to-128, 1-to-256, 1-to-1024, I think, and 0. 1, 2, 3, 4, 5, 6, 7, 8. Those are your 8 choices. So now I run this into my timer, and I can control how fast it's running. Right? So I did a spreadsheet the other night, so I could have this. So this little spreadsheet called Timer Math. If my prescaler is at 1, that means my count rate 16 megahertz. And if I'm on timer 0, which is 8 bits, my max delay is 1.59 to the -5th. My maximum count's 255. And then it says, I said, okay, if I want a 1 hertz signal, I have to count this many times. That's bad. This register doesn't count that high. Well, can timer 1 do that with 16 bits? No. So 64 bits, no. 256. So if I do a divide by 256, my count rate is 62,500 hertz. My maximum count is 65,535. That means I can do a 1 second delay on timer 1 with a prescaler of 256, and my compare is 62,500, so it's almost the whole timer full. So you got to do the math. If you look in the data sheet, it shows you how to do the math. But it's this. So this is 16 megahertz divided by this, and then you got 255 bits, or 16 is 65,535. Divide one into the other, and that tells you how long it takes to get there, right? If it's divide by 1,000. If I divide by 8, that's 2. If I divide by 8, that's 2 million counts per second. Divide by 16, that's 1 million counts per second. If I have 255 counts, 255 counts divided by 2 million counts per second gives me seconds, right? So we all nod and say, yeah. I don't feel like doing math in my head. It's algebra, but...
And it's late.
And it's late, right? So now, I have my counter, and on my counter, I have a compare register, A, and I have a compare register, B. And these connect, actually. This is the symbol for an AND gate. So remember, and, if this and that. This is all 8 bits, or all 16 bits, whichever one it is. And this could be 530, no it can't, it's only 8 bits. This could be 200, and this could be 156. And when this goes tick, 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 and gets to 156, bang, he goes 1 for 1 tick, and then he goes back to 0. And when he gets to 200, bang, he goes to 1 for 1, whichever prescaler clock tick, and then he goes back to 0. So you can imagine right off the bat that if there was an interrupt that you could tie to that and say that every time that happens, I want to go into this interrupt and do something, I could set this up on the 16-bit timer here, because we already figured out I can do 1 second. I can do this interrupt to do my half-second tick. You have to do some math to figure out exactly what the right number of ticks is. I think it's 32,500, because I did this thing and did all the math the other night, right? And I did this quick little spreadsheet to do all the math for me, so now I have to just put in a number and it gives it to me. But it's easy to get the numbers backwards because of the way I did it and end up with the wrong number. But anyway.
But you do the right math and you set it up the right way. You attach that to the interrupt, and your timer becomes your button press or your delay.
Right. So now let's get to some of the things. So this is mighty setup. We'll put it down here so that you poor folks on the at home can see this mess. So in setup, I did all my inputs and outputs, and then I wrote this function called enable the timer with a delay that's 31,250. So I have this defined delay 31,250, enable timer delay, and I come down here to enable timer, and now you see me doing a lot of bit manipulation. So TCCR, timer counter control register 1A, timer counter control register 1B. There's 2 registers to control that timer. Those controls, 3 of those bits are the prescaler. 4 of those bits are the mode, and 2 of those bits are something else that escapes me right now. That's the clock select. That's the mode. Oh, yeah, there's some sub modes. So what you can have happen is one of the modes is when I see the number. So if this one, I see that, here's a game I can do. I can say, I count, and when I get to 156, I set some bit high, right? And then when I get to 200, I set some other bit high for one quick count. And then the timer overflows and goes back to 0, right? 255, now 0, and it does this again. And then out here I see this bit happen, and then I see this bit happen. Now you can imagine where that could be useful, right? I know that these are going to be exactly this far apart. These 2 signals are going to be this far offset from each other, and they're always going to walk that way. if I'm lighting lights in a certain sequence, if I want them always to happen at the same time. That's something useful. The other thing I can do, so one of the sets of modes is that this actually connects directly over here to one of the port pins. And as soon as that happens, it turns it on and then turns it off. So I can get this little boop, 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 boop on the outside world. One of the other modes is it toggles that pin. So that means what I would see on that output pin is I would see high, low, and high, low. And those are going to walk that way together. Also potentially useful. One of the modes says either one of these, as soon as I see it, I clear the timer. So now if I redraw this mess, this is 156. This is 200. So I say, whenever I see this, turn it on. And whenever I see this, reset the timer. So now I count. I hit 200. So out here, this bit toggles. But now here, this drops. And now we go up again. And we can actually time this. We can set this up so that this does this. And so now this has the frequency of this, but the pulse is changing. So if I change this to 100, and move it down here to 100, we can see that this pulse is on for a longer time, but it's the same frequency. This is called pulse width modulation. This is how you make an LED brighter or dimmer. Because an LED is only all the way on or all the way off. Well, I'm telling you a lie, like I often do. An LED generally on a digital pin is always either on or off. And if you turn it on, it's really bright, but its energy over time is power, right? So the human eyeball integrates. So when you look at it, if it's like this, you don't even see that it came on because there was not enough energy there to trigger your eyeball to say that there was any energy there. But if I turn it on just long enough that my eye can start to register it and then I shut it off, but then I turn it on again just enough, then it comes on and it looks really dim. And then I can get all the way to the point here where these are on light. You know, they might tick just a little bit, but they're basically on all the time, and it looks really bright. I can adjust the brightness of my LEDs this way. This is how you make an RGB, change colors. You make the red a little dimmer, and you make the green a little brighter, and it shifts your color spectrum, what you think you're seeing off one way or the other, playing tricks on the eye. And I haven't done any of this here, but I have done it other places. And I think I pointed out the one week the color table, the chroma table. That's what you're doing. You're moving around on the edges of that, and it's causing the colors to move in and out on your eye. That's how TV screens have worked since they were color. That's how this works. If you go in there and look, there's a red, green, and a blue, red, green, blue, red, green, blue, and a Bayer pattern probably. So it's like, which is actually red, green, blue, blue, red, green, blue, blue.
Yeah, some companies have different patterns based on their
This is
technology,
the
but
Bayer
yeah.
pattern because
Yeah.
here you've got a red, green, and blue, but there you've also got a red, green, and a blue. So you can play games where you can blend colors in between it and make it look better.
And as long as you have it more than faster than 60 hertz, it doesn't look like it flickers much.
Actually, so the human eye is a wonderful thing. I have done My entire thesis back in 1998 was on making electronics that mimic the human eye. Okay, so the central part of the fovea of your eye is not real responsive to motion. The fovea of your eye can detect 30 hertz. Darn, I didn't get any of that on the screen because I was busy looking at the other screen. So your eye can detect at about 30 hertz is where it becomes imperceptible for the most part in your direct line of sight. I think movie theaters, the films are at 25 hertz.
The old school film were 24.
Or maybe.
Yeah.
So
Yeah.
it's pretty good. At 60 hertz, you can't really see it. But you can see it off over here. Because this part of your eye sees motion. That's the whole deal. If you move your hand over here, I can't see my finger, but as soon as I do that, I can see my finger. Because, oh my God, there's something moving over there, and we need to look at it in case it's a bear, right? No, I can't see it, I can't see it. Oh, I can see it, shit. There's a mountain lion, right? You know, something's sneaking up on me, I need to know that. There's a pirate there, I don't know.
Sure.
Tonight is apparently a pirate night. What you'll notice is here's a game you can play on your drive home if you haven't noticed it already. New cars have LED taillights, and they PWM them. They've got the dim mode where they're doing this, where they're on maybe 50% duty cycle, and then they've got their full on mode where they're full on. When they're driving down the road and they're not hitting their brakes and they're a ways in front of you, just look like this. And what you'll see is their light go
Yep.
and you'll see like 5 of their lights. And that's because even though they're blinking them at like 1,000 hertz, they're far enough away that when you look, that tracks across different parts of your eyeball. That's called persistence of vision. That's how you see the little clocks, the spinner clocks that write shit in the air, and that's what they're doing. It's the same thing as the tail lights. That's what you're doing here. It's a game called persistence of vision. So we're going to this horrible, awful code that I've written here with all these timers is setting that timer up. So that I have an interrupt vector. Now here's the first problem is that you can't attach an interrupt. So when you're doing these things, what I just did here, I could not use the Arduino built-in libraries. I think there are some out there. I did some research. There's like a couple of timer libraries that let you do some of this, but I didn't download them and dork around with them and try and learn them. I just went straight into hardware, and I'm mashing bits in the hardware. And if we load this in, we'll see this has basically the same effect as when I was using the timers to count these and blink that at the same time, except that.
Oh, it's broken.
The hell was that? Right. Yeah, it's going. So this LED is being run off of a timer interrupt, and these are counting at just using the delay in the main function. Now, so that at the first level is sort of true, but remember, I'm always lying to you. It takes time to go over here and service this interrupt and come back. And here on my screen, oh, come on.
You might have to open it again.
This is an oscilloscope display. So I had my oscilloscope tied onto the fastest one. So it's going on, off, on, off, on, off, on, off, on, off. An interrupt happened, on, off, on, off. So you can see I dropped,
Quite a few cycles.
I dropped probably one, maybe 1.5. So it took me 200 milliseconds, 150 milliseconds to go in there, do that, come back out. So he came on, and this time, he's busy. Couldn't do anything. And then somewhere in here, you know, if I take this 500 milliseconds out of there, he should have gone down there. So there was that much time that he was off servicing that interrupt, doing whatever it was he was doing. And then he came back. You can't see that here, but and even there, I mean, you see how many there were before that one happened. So, but it is happening. We haven't made a panacea that cures all ills here. It's happening. I could also have set up a second interrupt, right? I could have this one running at 1/2 second and this one running at 1/10 of a second and have them both running. But then you can have what's called an interrupt collision, right? This one interrupt, I'm still doing it. Well, that one happened. And so now,
Yeah, interrupting and interrupt.
right. So when you're doing this in the Arduino environment, when you're running time-sensitive code, that you want to say, you can't interrupt this, you bracket it with no interrupt, and then interrupt. I think that's right. Thank you. So what no interrupt does is it goes to the status register, which is a single register. There's a single status register, and one of those 8 bits is global interrupt enable. If that is set to a 1, then interrupts can happen. If that is set to a 0, no interrupt can happen. So interrupts have a priority. This, if you know, you've got one time tick where you latch all these interrupt requests. There's 2 registers that are your interrupt vector flag. I think they're IVF registers, and so you could have 3 interrupts happen at the same time, right? Because it's all random processes, and statistically, eventually 2 of them or 3 of them are going to happen at the same time. They have priorities, and generally speaking, you know, interrupt 0 happens first, interrupt 1 happens first, interrupt 2 happens first. But if you are in the middle of an interrupt and an interrupt happens, then you'll stop the interrupt you're in and go service that other interrupt. So if you're in a really busy system, you can get tits deep in interrupts, and you're eventually going to bomb your stack. Because remember, I was talking about you push these things off and you push things off. Well, it takes time to do this, and eventually you can just run out of time. We had a little thing we did at work. I built the board and we did the software on it, and we were bombing the interrupts. We were bombing our timeline. We couldn't keep up with how fast the interrupts were happening. So we had to do some changes to the code to simplify it. So what you do is you go into your interrupt, ISR, interrupt service routine, and it's some number. And this is what was run. Remember, I was telling you this ran me up the wall the other day because I had it misspelled. What is it? Capital timer 1 under count.
Copy.
Count A underscore lowercase vect.
Mm-hmm.
That, I think, is 12. That maps to 12. That in the list over here I had of all the interrupts, of the interrupt vectors, I think that's 12. And I had not capitalized all of this. I had a capital T, capital C, and all the rest were lowercase.
It says comp on there.
Comp A?
Am I misreading it?
Yeah, no, you're right. Comp A.
I didn't know if you were correct on the board and wrong on the
No,
code. or
no,
the
no.
other way around.
Other way around. That's what was causing all my problems. So when you, so in my down here, so here I set output compared to off, so that's the one that, if output compare is turned on, when I match that timer value, then I make a pin come on. Or I toggle it, depending on the mode. So I turn that off. I don't want that affecting my exterior pins. And they're on specific pins. So timer 1, each of these 3 timers has 2 compare registers. So that means there are 6 compare registers. That means there are 6 pins that can be affected by these. And if you look at your Uno board, if you were to lean over here and look, see pin 3, 5, 6, 9, 10, and 11 have that little tilde or whatever it is in front of them. Those are those pins. Those are the pins that you can do PWM outputs on.
Yeah, they're on ours too. Yeah. Little
Can you focus?
9, 10, 11,
Can't quite
5,
focus there.
6, 3.
There we go.
Oh, on the side?
Yeah. I don't know if mine are. I don't know if mine are on the sides of the pins or not. I can't. Yeah, they are. So, but right here, 3 has a tilde, 5 has a tilde, 6, 9, 10, and 11 each have tildes. So if you notice here on my little stripe, it says PWM is what the tilde is for. Those are the 6 register output pins that you can affect. And on yours, since you've got 6 registers, you should have 12 of them probably.
Yeah. Here's 1, 2, 3, 4, 5, 6 on that side.
And notice how I've commented these so I can tell you what these different pieces of code do. So here, the set that's highlighted, I've turned off those pins. This section of code here that's highlighted, I'm clear. Whenever I get a match with OCR1A, I clear the timer. So this is what I was talking about. I just started over. That way I have a known time. That's my frequency that things are going to happen at, right? And here, these 3 lines of code, I'm setting my prescaler to 256. So let's talk about these for a little bit. These are important things. We talked about the and equal. So, come up here to the board.
You done with this? Did you get yours? Your new one's not.
So we talk about running an interrupt inside of here. So if I come into my interrupt service routine, I'm jumping back and forth, I realize. I say no interrupt. So now that I'm in here, if another interrupt happens, it won't interrupt my interrupt. So I could have 3 or 4, I could have a timer 1 comp A vector, and I could have a timer 1 comp B vector, because I have 2 compares that I can do, and I can set an interrupt on either one of them. So I might want to have 2 of them, but I want to make sure that they don't interrupt each other. So this is time critical. Yeah, this one's dead. We can say this is time critical code that's going on in here. I don't want it interrupted. And now at the very end, I turn interrupts off. I mean, that is the last thing I do before I exit.
Enable interrupts again.
Yeah, and it's like a GEI, Global Interrupt Enable, GIE.
So with no interrupts on, does it queue potential interrupts to process
Yes.
after?
Yes.
Okay.
So over here, my IVF flag, my IVF register has these interrupts in it, right? And so I went off to service this one, and when I went in, I cleared it. And the truth is, 0, 1, 2, 3, down to 8, that's usually the priority order too. So this one went, I came in and did it. As soon as I went in there, I erased it. I'm servicing this interrupt, it's not interrupt anymore. But I said no interrupt. While I'm in there, 0 happened. Well, bing, 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 I come out, that's actually a lie. 0 is usually called NMI, non-maskable interrupt. If that one goes, by golly, you service that one no matter what. You can't mask him out. But so we'll say 3 happened. 3 happens, I go all the way through, I say, my very last step is, I'm done doing interrupts. Oh! The guy over here, this crazy guy, the pirate who takes over your program counter says, but he's there! And now you run over here and do this other one. So now you forced this interrupt to wait on you on the other. You gotta be careful when you do those things. Because now you're diddling with time and the way things happen in time. And you have to you don't want to shoot yourself in the foot. You want to take really careful aim before you shoot yourself in the foot. 16 megahertz at an instruction per cycle, you're cooking along pretty fast, but you can have some unintended consequences come out. And you're just like, you sit there and look at it and say, I don't understand what's going on. Take a look at your interrupts. If you're running multiple interrupts, take a look. Just make sure they're not walking on each other. And there's ways that you can test that. And you can, one of the things you can do is as soon as you get in there, you can have it light a light, and you can look at it on an oscilloscope and watch pins go high and low and say, oh, well, that's kind of messed up, or whatever. And since you guys have a scope out here.
A little pocket scope somewhere I'll dig up at some point.
Yeah, so let's see, where was I going? So we've got where was I going? I've forgotten where I was. Talking about interrupts. You service the interrupt. There's a table of these. They're not on the Arduino site. The table is in the data book, or in the data sheet for that. And when I say data sheet, it's like 300 pages. But it's a nice PDF, and it's got, it's got the newer PDF stuff where it's got chapters and stuff down the left side. And you can just click and it'll take you there. Or you can just say, do a global search, Control F, and search on interrupts or whatever else. So we have this idea of interrupts. Now what you want to do is you want to rely on the hardware as much as you can. Because these little pieces of hardware are all off running on their own. So I've got this, remember I drew with the compares and everything else. I've got timer 0. I've got this hunk of hardware out here on the address and the data bus. And when you go out and all this stuff that I wrote over here and told it to go do it on its own, it's off doing it on its own. All that counting, all that stuff, that's not a process that I have to maintain. I only have to set it up and tell it, go do it. Now when that interrupt happened, I had to come service the interrupt. But a lot of these PWM things, I don't have to do it through an interrupt. It'll do it automatically. And so that's going to be our homeworks for 2 weeks from now. Yeah, that's a reasonable time, 2 weeks from now. So what I'm going to have you do is use how do I want to do this? The first, okay, we'll do this. That work, millisecond on. Not sure that's fast enough. Take a look, I think there's a delay microsecond function. and do. So I just want you to do. I want you to do a coded PWM. So what you're going to do is delay.
Yeah, delay microseconds.
Was it delay US?
Delay capital microseconds. If that's the one you're looking for.
And here's what I want you to do. I want you to do. I'm just doing this off the top of my head, so this might not quite work. So we'll do byte count equals 0. In loop. Do a digital write. I have to think about this. Digital write. Out pin. High. Digital write. Out pin. Low. Delay. Microseconds. $250. Let's do 300. Count plus plus. Doing this off the top of my head. What this should do,
Fade up.
we'll start out with count equals 0. So we'll go high,
Oh, fade down.
and then we'll go low. And so it'll just be on for really, it can't go all the way to 0. It's always going to come on for like just a couple of ticks. But then we're going to wait 300 milliseconds, microseconds. No. 300 minus count. That's what you want to do. Delay microseconds, 300 minus count. So what that should do is, it should come up. So on your first pass through, you'll see this. This is like 1 tick. So this will be like that. Yeah, boop, on off. It won't be a thing. And then 300 microseconds later, so we'll call this 300 microseconds. It basically comes back around to here, right? Because you're just looping through this over and over. And now it goes 1 tick, and then it'll go 2 ticks, and then it'll go 3 ticks, and eventually it'll be high for 255 ticks. But I'm only going to stay, after I turn it off, I'm going to be low for this amount of time. So what you should see happen is if you've got an LED tied to that through a resistor, it'll get brighter and brighter and brighter and brighter and brighter and brighter, and it'll go off. And brighter and brighter and brighter and brighter, it'll go off. Brighter and brighter and brighter, it'll go off. And it'll happen fairly quickly. You might want to do this just delay.
Yeah. And will it go off? Count never goes back down.
Well, it counts a byte, so it's only 8 bits.
Ah,
So it'll go to 255, and
Gotcha.
then it'll wrap to 0.
gotcha.
Right? So you got to understand, this is the limitation of the hardware. I can
Sure,
only
sure.
count to 255.
Yeah, not used to that. Actually making use of hardware limitations. and not manually resetting things.
Oh yeah.
Yeah.
This is the games you play when you get down
Sure.
to here. So this is the first, and so this is what's going on. I'm asking you to do this as a conceptual understanding of what you're getting ready to tell this hardware to do. Now, then the I don't know. They have a tone function. If you look at the reference library for the Arduino, for the IDE, there's a tone function, but I think that just does a 50% duty cycle square wave at the frequency you put in. So I'm not 100% sure. So if you put that in, it doesn't matter the speed that you're going to do it. If you do it really slow, you'll see it blink. But if you do it at anything faster than 30 hertz, which I don't think you can go that slow, you'll just see it'll be a medium brightness no matter what the tone is. So I want you to look up PWM and how to do PWM. There is something called the Servo Library that you can download. So we'll talk about that too. You might want to play with a servo. You can a servo motor is like what a remote control car uses
Steering and stuff.
for the steering. What it has is the motor has a natural position there, and you give it power, and you give it ground, and you give it a PWM. And when it's 0% duty cycle, it's here, and when it's 100% duty cycle, it'll be all the way over there, and when you're at 50% duty cycle, it'll be right there in the middle. So that is a great way to do a speedometer, right? You do a frequency to PWM conversion, and you can say, I'm going this fast, I'm going this fast. I'm going 50 miles an hour down the road. That means I want this to be at this position. A simple math equation to say what my percent duty cycle needs to be. It's at, if my maximum speed's 100, that makes life really easy because 100% duty cycle is 100, 0% 0, 50% duty cycle is 50. Right square in the middle. You tie a needle to it and you can run them back and forth. So I invite you to look up stepper motors and maybe hook one up and drive it.
And servo. Servo, not stepper.
Servo.
Yeah.
What did I say? Stepper?
Yeah.
Servo.
I heard stepper. That doesn't mean you said
Servo.
stepper.
Hook up a servo motor.
Yeah.
You can drive a servo directly. A stepper you cannot drive directly. Stepper you need special. Figure out how to. So we've done this. Figure out how to go out and diddle the hardware to do this for you, so that now you can make your light be whatever color you want it to be. So or not color, brightness. What you can do then is you can say, what. So the way you'll do the PWM, remember we talked about the timer, and we talked to the compare register, and they get ANDed, and stuff happens based on that. What you can do is once you get this all set up, then in your main loop code, off over there, you just increment and write. You say, oh, Comp A is now 1, Comp A is 2, Comp A is 3, Comp A is 4, Comp A is 5. And what you'll notice is that the LED to your eye does not get bright linearly. It's dim, 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 gets really, really, really bright, and it kind of hangs there, and then it goes away. That's because your eye has a logarithmic response, and you are giving it a linear response. If you'd like to look up that, I've actually done some research and posted some videos on it. For 255 counts to stay linear, it's only 12 steps. So if you went from here to here to here to here to here, it would look like it went up the scale in gradients.
Right.
You'd see these big chunks, pop, 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 but this one would look twice as bright as that one. This one would look,
Right.
or 1 times bright, 2 times, 3 times, 4 times, 5 times bright.
Not linear.
Because the response of your eye is this,
Right.
and your brightness scale is doing that. So you've got to choose points here that land
Didn't match with your eye.
that land on, yeah.
Cool.
So let me write this down. Homework 1, that coded PWM. Homework 2 is use timers to PWM an LED. And then bonus points, homework 3, control a stepper, servo.
Eventually. Sounds good.
Think we're good?
10 o'clock, yeah, I think.
Holy shit, it's 10 o'clock. Wow, I went late tonight, didn't I?
Yeah,
Was it too much?
yeah.
Yeah.
My brain